Last time we talked about enthalpy and how that was a measurement of the heat energy in a system. Today we're talking about calorimetry and molar enthalpy. So what is calorimetry? Well, if you go back to that drawing that we had initially where we had the system and we had the surroundings. If you put a thermometer into that, you're doing calorimetry. So calorimetry is used to determine the amount of energy that a system and the surroundings traded. So if you kind of go back to this one just for a second, and I'm sorry if you were already starting to write down the next bit, but if you go back to this diagram for a moment, all of the energy is going to be contained within the surroundings. So if we can trap it all in a small surroundings, then any energy change that there's been between the surroundings and the system, whether it's energy in or energy out, then we can figure out how much energy the system changed by figuring out how much energy the surroundings changed. All right, back to here then. There's a concept of specific heat capacity, and that is the definition that you see there. And then the formula is specific heat capacity is the energy over the mass and over the change in temperature. And if we know the specific heat capacity of the substance, then I can use all of that to determine the energy by rearranging the formula for energy. So if I take that as the surroundings, because no matter what I do, it will always be part of the surroundings, then the system will be the opposite. I might not be able to know the specific heat capacity or the change in temperature as such of the system, but I know that whatever the surroundings did, the system will have done the opposite. So in other words, if the system, or if the surroundings, let's go that way, if the surroundings gains 100 joules of energy, that means the system lost 100 joules of energy. On the other hand, if the surroundings loses 100 joules of energy, that means the system gained it. So this middle line here about the energy of the system is equal to the negative energy of the surroundings, that idea is going to be extremely important as we're doing calorimetry. And then for us, what we're going to make sure that we can do is that the energy of the surroundings is calculatable by, it's English, I can make up any words I want, calculatable by specific heat capacity, mass, change in temperature. Now we need to be cautious about this mass because if we're talking about the surroundings, then it has to be the mass of the surroundings. Okay, moving on. In calorimetry, this is what we're trying to do. We're going to take a temperature change of a known surroundings. So we'll have usually water. It'll be a solvent, it's a good heat sink. We'll have water, we'll know exactly how much mass of water we are using. Then we will know it's water, so that tells us our specific heat capacity, and then we'll measure the temperature change. And once we have all those three, we can calculate the energy. Then we will relate that to the enthalpy change of the system. But we also have to be careful to make sure that we convert it into numbers of moles because it is going to be the molar enthalpy change of the system that we're after. Okay, so we'll do an example. Okay, data that we're going to take, it's going to end up looking something like this. We'll have a volume of water. However, nowhere in our formulas did we use volume, but we'll use, in this case, 10 milliliters. 10 milliliters of water has a mass of 10 grams. We'll have a mass of, in this case, lithium bromide, but we'll have a mass of some system. So that, we're going to leave that later, or we're going to leave that till later, I should say. So ignore the 0.5 grams for a moment. We're going to measure the temperature at which the water started. We're going to measure the temperature at which the water finished. And then we know the specific heat capacity because it's water. Then what we do is a calculation that looks something like this. So negative energy of the system equals the energy of the surroundings. Well, before I have the negative on the other side, it's okay. As long as I remember to change the sign at some point. Right now it's more convenient over there because I don't need it right now. It's just going to clutter things up. So I do my calculation, and again, notice that the mass, that middle term, is 10 grams, not the 0.5, because the 0.5 represents the system, and right now I'm working with the surroundings. Once I bring it down to a nice neat number, then I'm going to flip the sign over to the other side. This because the surroundings, because it went up in temperature, it gained energy. That means the system lost energy. Too easy. Okay, but that was for 0.5 grams, and I need this to be in molar amounts. So now that 0.5 grams, that's the system. I'm going to deal with that. So I take that mass and I first figure out how many moles that is. It ends up being not a very large amount of moles, but that doesn't matter. Then what I'll do is I'll take the energy that I had, the negative 146.3 joules. That was the energy for that small amount. Well, divide that by the number of moles, and I will have a joules per mole. Now, most often, these numbers are more convenient to express in kilojoules per mole, which just means I divide the joules per mole, divide that by 1,000 to get kilojoules per mole. That's all there is to it. Now, I can also expand that into a different kind of reaction. So the first example wasn't really a chemical reaction. It was more of a physical reaction, just dissolving something. So here, now I would have to be careful to decide whether or not I want to represent it as this is an acid-base reaction, but I could represent it in terms of the HCl, hydrochloric acid, or the sodium hydroxide, NaOH. 1-to-1 molar ratios, it won't actually matter. Similar kind of data table. I've got an amount of water, I've got an amount of acid. I have a way to calculate the number of moles of acid between we've normally been using capital C rather than M. I've gone old school on this. So it used to be called the molarity, but the molar concentration of hydrochloric acid, and then the molar concentration of sodium hydroxide. Okay, now we do a similar calculation. We're going to figure out the energy of the system. That is going to be the the solvent, the water. And because these things are fairly dilute, then the specific heat capacity of the solution will be pretty close to this. It will probably be almost identical to the specific heat capacity of the solvent, the water. So I'm going to use that 4.18 joules per gram per degree Celsius again. Also, the mass of solute that I have added to the water really won't change the density. So 1 gram of water would have a volume of 1 milliliter, and 1 milliliter of this solution would have a mass of about 1 gram. So I can still use that 1-to-1 ratio again. So, similar calculation, I figure out the energy of the surroundings, I convert that to the energy of the system simply by changing the sign, and then I've got, in this case, negative 292.6 joules. But I'm going to relate that to, what am I relating that to? The acid, there you go. I'm going to relate that to the acid, so I'm going to use the molar concentration and the volume of acid, and I'm going to figure out what that is in terms of numbers of moles. Then I'm going to take the energy of that sample, the small system that I had, and I'm going to divide that energy by the number of moles to figure out the molar enthalpy of that reaction. And again, it's going to be more convenient to represent that as, or express that, second time, express that as kilojoules per mole, and we end up doing that. So negative about 58.52 kilojoules per mole. All of the calorimetry calculations are going to actually be fairly similar. You're going to have, in most cases, water as your main place where the heat energy is going to go to or going to come from. So that is almost always going to be your surroundings. When we do a lab, we're actually going to add one piece to the system, sorry, not to the system, to the surroundings. And I've seen a question or two in your textbook where there's another piece added onto your surroundings, but again, you just add it on. It doesn't become any different. It just becomes one extra little piece that is adding one other extra thing that is absorbing heat energy or providing heat energy. And then we always figure out how many moles that we have. And again, the only real caution that you have is make sure that when you're looking for the specific heat capacity times mass times change in temperature, that mass has to be the surroundings, which is almost always going to be water. Anyway, we'll do a bunch. We'll do some for as a lab, and then we'll add on to this once we know better know what's going on. Talk to you in class.